Hello everyone. I hope you're all doing well and staying safe. So we're going to solve a problem on the idea of collisions. Okay, so this is our first problem on collisions using the idea of linear impulse momentum and angular impulse momentum. So we will start off with a fairly gentle problem, and I'll walk you through the problem and the different steps that are involved in solving this problem. Okay, all right. So here is the problem. I have a pendulum. I'm going to draw that, and this pendulum has a fixed pivot here, and initially this pendulum is at rest. Okay, so this is the initial position of the pendulum. Here is the bob of the pendulum. Okay, so initially let's say that the pendulum is at rest. So initially the pendulum is at rest. Okay, then what happens is that there is a small stone or some kind of a silly putty. Let's assume it's a silly putty. Okay, that silly putty that comes and it strikes this pendulum. Okay, so somebody is throwing a stone at this pendulum, and let's say that okay, this is going to be a different kind of a shade inside here. So I'm just going to think and see. Okay, now let's think of it this way. So probably I did not do the fill properly. Okay, all right. So in this case, this stone or this ball, let's say it's a ball. Okay, it looks like a ball, right? So let's say that this ball is traveling towards the pendulum with a certain velocity. Okay, so I'm going to draw the velocity of this ball here. Okay, so this ball is traveling towards the pendulum with a certain velocity, which we will call as v naught. Okay, so ball, and let's say pendulum, let's label it as p. Okay, and then this is the point O, which is a fixed pivot, and then this is the ball B. Okay, so the pendulum P is at rest. So let me scoot this over a little bit. That's the nice thing with these things, I can always come in and add some stuff. I don't know. Okay, maybe I'm just doing a free advertisement for Notability here. All right, I don't mean to do it that way, but here is the idea. So the ball B comes and strikes the pendulum bob, pendulum P. Okay, and then sticks to the bob of the pendulum. Okay, so this is traveling with a certain velocity. Okay, and then so there is an impact takes place. Okay, so which means that this is an impact event. Okay, and then what we are told is, okay, it's not like the pendulum is just going to sit there silently, right? It's going to take this silly putty or this ball which comes and stick to the pendulum, and then both of them are going to start swinging. Okay, and what we are going to be finding out is the following. So once the ball hits this one, so let's see like a sequence of events. So this is initially what is going on. Okay, so let's say that this is initial. Okay, then there is something a situation where the collision takes place. So let me copy all of these again. Okay, and then let me just redraw it here. Okay, so this is where the collision is now taking place. Okay, so this is collision, impact, and then what's going to happen, these two are going to stick together, right? Which means that after impact, so this is the pendulum P, this is the ball B. Okay, both of them are going to start swinging together as a unit. Okay, as you can see here. So I'm just going to copy these two and then paste it here and then bring them together here. So they're both going to start sticking with each other and then swinging. Okay, so then that's what is going to happen here. So right after impact, everything is going to start swinging. Okay, and I'm told that okay, this is an angle theta. Okay, what I want to do in the problem is the following. Okay, obtain a relationship between the initial velocity of the ball V naught and the maximum angular deflection, let me write that properly, of the pendulum ball system theta max after the collision has taken place. Okay, and we are also told that the mass of the ball is a little m, and then the mass of the bob of the pendulum is 2 times m. Okay, so I'm just going to write that down here. Okay, and so the mass of the pendulum is 2m, and then the mass of the ball is given to me as little m. Okay, so this is information that is given to me. So this is the mass of the pendulum, here is the mass of the ball. Okay, the pendulum strikes with an initial velocity. Okay, so here is the initial velocity of the ball, and we need to find out the relationship between V naught and the maximum angular deflection of the pendulum bob or ball system after the collision has taken place. So if I call this angle as theta max here, okay, I need to find out the relationship between V naught and theta max after the impact has taken place. Okay, so this is the problem, and we are told that these two ball and the pendulum bob, they stick to each other. And how do we solve this problem? Okay, so here is the situation. You want to think of this problem as two things or two separate problems. One is there is an impact event taking place. Whenever you solve for an impact problem, you will use the quantities of linear impulse momentum and angular impulse momentum. You'll use those techniques. And then I'm going to say, okay, after the impact has taken place, they're just swinging from one point to the other, so I can make use of work energy principles. Okay, so here is my strategy for this problem. Okay, so strategy. Okay, so break the problem into two pieces. Into two parts. Initially is the impact part, impact between ball and pendulum. Okay, the key word is whenever you see impact or a collision, okay, impact or collision, okay, we will handle this. Use, let me maybe write it down here. So we will handle this using the concept of linear impulse momentum principles. My shorthand notation is LIM principles and angular impulse momentum. Or AIM principles. Okay, so this is the first part of the problem. Okay, so whenever you hear the word impact, your first motion should be thinking about linear impulse momentum and angular impulse momentum. Okay, then we will say, okay, after that part of the problem has been handled, okay, so after impact, the bob and the ball travel together to a position of maximum deflection. Okay, so we will handle this using work energy techniques, using the work energy theorem. Okay, so that's the other thing that we're going to be making use of. So this is almost like a combination problem, two things are being asked here. Okay, and so this is the situation after impact. Okay, so the impact event itself is going to be modeled using linear impulse momentum and angular impulse momentum equations. And very quickly, let me go back and say that the length of this bob of the length of the pendulum is 2 meters. Okay, so this is going to be 2 meters, and likewise, okay, so this is a length of 2 meters. Okay, all right. So and this was the initial situation where the ball was traveling, and then there is an impact taking place, and then this is after impact. Okay, so this is after, or let me write it down right next to it, after impact. Okay, so we have everything going on here in this problem. Fantastic problem. You're going to be seeing something very similar in terms of other collision problems that we're going to be solving. Okay, first step is to look at the impact event. Okay, so first, so model the impact event using the linear impulse momentum and angular impulse momentum equations. Okay, so that is our first step, and we're going to be drawing some very special diagrams. Okay, so whenever you have an impact problem, you're going to be drawing what is called as a momentum diagram and an impact relevant free body diagram. Okay, so for any impact problem, we shall draw a momentum diagram okay, which I'm going to call as MD, and then we will draw an impact relevant free body diagram, which I'm going to call as IRFBD. Okay, so this is also another key statement that you're going to be making use of. Okay, and momentum diagram. On the momentum diagram, you mark all the linear momentum quantities. Okay, on the impact relevant free body diagram, you will mark only those forces that are relevant during the impact event. Okay, so that's typically what you're going to be doing, and I'll be talking a little more on what we will be doing in the impact relevant free body diagrams and so on. But first, let's also, one more thing that I want to say is the impact event itself. Okay, the impact event takes place over a very short duration of time. Okay, so almost infinitesimally small duration of time. Time duration. So what this means is that if I say T1 is the time right before impact, and T2 is the time right after impact, Okay, then the time interval, so t2 minus t1 is approximately 0. Okay, so this is going to be very, very small. Okay, so that is the meaning of what I'm trying to say here. Okay, so t1 is the time right before impact. Well, that did not come out as a straight line at all, right? I mean, that, what was that? I'm not even sure what that was. Okay, so t2 is the time right after impact. The time duration of impact is very, very small or infinitesimally small. This is something that is very, very important to notice. Okay, so this is extremely important. Well, okay, and depending on how long the problem is going to take for me to solve, I might even break it up into two pieces. Okay, I'll do the impact first, and then I will look at the work energy principle after this. Okay, by using after the collision has taken place. Now I'm going to draw the momentum diagrams and so on. Okay, so here are the two things. So at time t1, I'm going to draw the momentum diagram. Then I'm also going to do that at time t2 and write down it. I'm going to draw the momentum diagram. Okay, and let's underline these two guys. So at time t1, then at time t2. Okay, and so what is the situation at time t1 and at time t2? So let me go back and bring out my creatures from here. So I'm just going to copy it. Okay, look at this. Okay, I'm just going to paste it right here. Okay, so this is the situation. Now on the momentum diagram, you're going to be drawing the momentum, right? Which means that for me, as I'm drawing the momentum, I'm essentially going to be drawing the momentum of the particle. Okay, so here this is going to be mass times mv naught, which is the mass of the ball times mv naught. So instead of drawing it there, so here is typically how I do it. I will get rid of this entire guy. I don't need that here. So right where I have the bob or the ball, I'm just going to draw this in this direction here. Okay, so this quantity is going to be mass of the ball times velocity of the ball. Okay, or velocity of the ball, which is v naught. Okay, so this is the initial velocity which we do not know, and at this point in time the pendulum is at rest, which means that its mass times velocity is going to be 0. Okay, so I don't have any mass times the velocity of the pendulum is going to be 0 here. Okay, so this is the velocity of the ball, here is the velocity of the pendulum, this is right before impact. Okay, so this is right before impact, and what I'm showing here is that actually the distance between the ball and the pendulum is very, very small, because the impact is almost going to take place, right? But I'm not showing that here. Okay, so I'm exaggerating this distance here, so maybe let me make a small note here. So I'm kind of exaggerated distance. I'm not sure how many g's and how many x's. Let me try. Exaggerated distance. Okay, in reality that is infinitesimally small. Okay, I hope that makes sense. So the ball is about to hit the pendulum bar. Okay, then I'm going to draw the momentum diagram right after impact. Okay, so this is at time t2. Look at this. Okay, so I'm going to have the same setup. I'm going to get rid of some of these things and you'll see why. Okay, so I'm going to have this same setup right here. Okay, but then here is the situation. Now I don't have that guy. Okay, this bob and ball, they are now sticking with each other, isn't it? Because we know that is the situation here. Now what is the velocity of the pendulum? That is not 0 anymore, right? Because the ball has struck the pendulum, so the pendulum is about to start swinging. okay, which means that it's going to have a certain velocity. Okay, so I'm going to write them down in the following manner. Okay, so this is going to be mass times velocity of the pendulum, which I do not know, so I'm putting a prime on it. And then this is mass times velocity of the ball, I'm putting a prime on it. Okay, so this is the situation right after impact. So this is right after impact. Okay, so this is right after impact, and then I have the situation right before impact. Let me bring that up a little here. Okay, and then let me do the underlining. I hope this makes sense to everybody. So this is the momentum diagram right before impact. This is the momentum diagram right after impact. Okay, then one more thing I need to draw is the impact relevant free body diagram. Okay, so let me do that very quickly. Now one thing that we will look at is this. Okay, so if I look at the force of gravity, okay, so look at the impulse due to the force of gravity. Okay, so if I look at the impulse due to the force of gravity, sometime t1 to t2, times mg times dt. Okay, so this is approximately, or not even approximately, this is mg times t2 minus t1. Okay, mg is a finite quantity. Okay, which means that mg times t2 minus t1 is approximately 0, because t2 minus t1 is approximately 0. That is, the time duration of impact is very small. Okay, I hope that's making sense. Which means that the force of gravity does not offer an impulse. Okay, so which means that the impulse due to the force of gravity is approximately 0. Which means that when we draw impact relevant free body diagram, we will not consider gravity to affect our problem, to offer any impulse, which means we can neglect it. Okay, so this is an important statement, and I hope you understand why this is the case, because the force mg is finite, which means that if I take mg times a very, very small quantity, then mg times that small quantity is approximately 0, because the time duration of impact is very small, and so the impulse due to the force of gravity is approximately 0. Okay, so what do you draw on the IRFBD? Okay, so what do you show on the IRFBD? Only the contact force during collision, and then you also show the pin reactions or support reactions. If any. No other force will be shown on the IRFBD. Okay, no other force will be shown or drawn on the IRFBD, and the reason for that is because the duration of impact is small, so that the impulse of any force except the contact and support reactions, contact force and support reactions, let me write that properly, is approximately 0. Okay, so which means that you don't show any other force on the impact relevant free body diagram. So if I draw the impact relevant free body diagram, it's going to be really easy for me. Okay, so look at this. I'm going to bring my figure from here, and then I'm going to collect all these figures and bring them all together again. Okay, so you will watch that as well. So I'm going to bring that here. Okay, so hang on while I clean up my act. Okay. So I'm going to cut that off. I'm going to cut off some of these things. I don't need the momentum because I'm not going to be drawing the momentum. Okay, so I'm going to draw the impact relevant. So this is the IRFBD. Sorry, this is the IRFBD during the duration of impact from time t1 to time t2. Okay, so I'm going to draw the IRFBD in a second. Now first thing is, when I'm showing a pin, I don't actually show this pin here, right? I have to get rid of this pin and then I have to draw the pin reactions. Okay, so essentially in this situation I'm going to have pin reactions, some OX and some OY. Okay, I don't know what the directions are going to be. Who cares, right? Because we don't know. This is going to be OY, this is going to be OX. And then what am I going to have? I'm going to have a contact force. The ball is coming and hitting the pendulum, which means the ball is going to impact the pendulum in this direction. So it's going to have a contact force in that particular direction. Okay, so this is going to be FC, but the pendulum is going to have an equal and opposite contact force back on the ball. Okay, so that is also going to be FC. So this is the impact relevant free body diagram during the duration of impact. Okay, so this is the IRFBD. I'm sorry. During the duration of impact. Notice that gravity is not put in here, okay, because it is not an impact relevant force. Okay, the impulse given by gravity or afforded by gravity is very, very small for the reasons that we just discussed. So we will not be putting that here. Okay, so I'm going to put all my figures back together. Okay, so put all the figures together. Okay, so I'm going to bring up my figures from here and maybe clean up some of them as well. Okay, so this is the momentum diagram. So let me just take only that. Okay, so copy this, then paste this here. Okay, I don't need that guy. Then I'm going to bring the momentum diagram right after impact. Here is the momentum diagram, so copy that and then paste that here. And I'm going to have the impact relevant free body diagram during the duration of impact. Okay, so I'm going to copy that and I'm going to paste that right here. Okay, so this is the IRFBD between time t1 and t2. Okay, so these are the three figures that I have to get my problem started. So one momentum diagram and then one momentum diagram at t2 and then the impact relevant free body diagram. Okay, so these are the things I have. Then the equations that are going to be useful for me, there are two sets of equations. Okay, so first of all, the main thing I want to talk about here, one thing before we move on, is that there is something called as a line of impact. Okay, so you look at this problem, the line of impact is directly going to be a horizontal line here. Okay, so this is called as the line of impact. Okay, so maybe let me write that in some kind of a dotted line here. Okay, so hopefully that's good enough for us. So this is called as the line of impact. Line of impact, or LOI. Okay, and the direction that is tangent to that or perpendicular to that is called as the tangent direction. Okay, so in this problem, I don't have anything taking place perpendicular to the line of impact. Okay, so for this particular problem, okay, so for this problem, we need not look at anything that is perpendicular to the line of impact. Okay, so that's something that I already know. And so what am I going to do? I'm going to make use of my equations. Okay, so what are our equations? I'm going to have the linear impulse momentum equation, which is going to be m times v at t1 plus integral t1 to t2, the net force dt is equal to the m times v at t2, which is going to be the linear momentum at time t2, and then likewise I'm going to have the angular impulse momentum, which is going to be r cross mv at t1, okay, plus integral t1 to t2, the net moment, okay, and this has to be at a particular point. Okay, so this is going to be at some particular point, so let's call it as point O. No, I don't know, some point. Okay, dt, this is going to be r cross mv t2. Okay, so that is going to be the angular momentum at time t2. Okay, so linear impulse momentum, angular impulse momentum, these are the equations we are going to be using. So for us, once again, okay, so lim is only along the line of impact direction in this problem. Okay, because I know that the impact event is taking place in the horizontal direction, and right after impact those two guys are sticking to each other, which means that this pendulum is at this point in time, it's about to start traveling. Okay, so if you want to think of it this way, it's about to start traveling along some kind of a circular path. Okay, let me draw this as a dotted line. So since it's going to travel at along a circular path, I know that the velocity at any point in time is going to be tangential to the path. So which is why I know that the things that are taking place in this problem are only along the line of impact and nothing else. Okay, all right, so I'm going to move along. Okay, so I think I need to have these figures once again taken to the next page, because I don't want to keep scooting back and forth. Okay, so if that is okay with everybody, I guess nobody's going to say anything because nobody is here other than me, but I'm just going to take it anyways. And with your silent permission, I'm going to bring it down here. Okay, so these are my figures. This is the impactor element, and then this is the momentum diagram. So this is momentum diagram at T1. This is the momentum diagram at T2. Okay. So my first step is this. Okay, let me start writing out the linear impulse momentum equation in the direction of the line of impact. Okay, so let me write linear impulse momentum, and I'm going to assume that the direction along the line of impact is positive. Okay, so what are my things? Okay, so this is a linear impulse momentum for the ball. Okay, so for the ball, what is the linear impulse momentum? So I'm going to see, okay, at time t1, what is it going to be? It's going to be mb times v naught. And then what is the net force acting on the particle between the time duration of t1 and t2? It's going to be minus fc dt, as you can see. Okay, and this is going to be m times v ball prime, okay, which is going to be the momentum at time t2. Okay, so this is the linear impulse momentum as applied to the ball. And then let me also write the linear impulse momentum, angular impulse momentum for the ball. Okay, so Angular impulse momentum. Well, before I do that, let me write the linear impulse momentum for the pendulum as well. Linear impulse momentum for the pendulum. Sorry. Look at this. For the pendulum, at time t1, what is the momentum? 0. Right? Which means that I'm just going to say, okay, hey, this is going to be 0. And then between time t1 and t2, what is the net force acting in the direction of the impact? Look at this very carefully. The net force acting in the direction of impact is going to be Fc minus Ox. Do not forget that pin reaction. And then I go to the momentum diagram at time t2 and I see, okay, what is the linear momentum? mvp prime. Look at the directions. Make sure you're careful with the directions. Here I'm assuming all things pointing to the right to be positive. So everything is pointing to the right for me here. One of the things, the contact force here is pointing to the left, so that was taken to be negative. Okay, so now I see, okay, if I add these two equations, so let me call this as equation 1 and then let me call this as equation 2. Okay, so equation 1 plus equation 2, what that is giving me, that gives me mb vb. If I add the summation inside the integrals, I'm going to end up getting minus integral t1 to t2 ox dt. This is equal to, this is the mass of the ball, so let me put that properly. So this is mb vb prime mp vp prime, and I think I need to make that connection here as well. So this is mass of the pendulum, mass of the ball, mass of the pendulum, mass of the ball. Let me also make sure that my figures here are right. This is mass of the pendulum, mass of the ball. Okay, and I guess I needed to do this probably here as well. So this is mass of the pendulum, mass of the ball. Okay, and I think that is also to be drawn here. Okay, so we're good to go. If I do this, I see that this is the situation, which essentially tells me that linear momentum is not conserved along the line of impact so far. Okay, it's mostly because we do not know what integral ox dt from time t1 to t2 is. Okay, if I know that this is 0, then probably it is conserved. Who knows, we can find out if necessary. Okay, so that's one thing. So this was not a good thing to do because it led me to a roadblock. I cannot proceed further. So what am I going to do next? I'm going to look at angular impulse momentum. Okay, so next step is okay, so now look at angular impulse momentum. Okay, so choose a point for the system. Okay, so choose a suitable point to apply angular impulse momentum. Okay, so what is a good point that I can choose? My strategy is this. I'm going to choose a point by looking at the impact relevant free body diagram. When I look at the impact relevant free body diagram, it looks to me that this point O is a really nice point to choose, right? Because if I do the summation of moments about, the pin reactions are going to vanish. They're not going to be a part of my angular impulse momentum equation. Okay, so I'm going to choose the point O. Okay, because we then need not worry about OX and OY. Okay, so let me do that, and let me do this very carefully by probably bringing back some of my figures once again to the next page. Okay, with your permission once again. Okay, alright, so I'm bringing my figure here and I'm going to look at the angular impulse momentum for the ball first. Okay, about the point O. Okay, so angular impulse momentum So this is for and we're going to assume that all counterclockwise rotations are going to be positive. Okay, so I'm going to do it for the ball about the point O. So first things first, look at the linear momentum of the ball. Angular momentum is the moment of the linear momentum, which means that it's going to be the momentum mv0 multiplied by a moment arm. Okay, so look at this. What is the distance? So let me take this creature and then put this creature down here. Okay, let me also do the same thing. So that is going to be somewhere here, or this is okay. I think this is okay. So look at the ball here. Okay, so if I look at the perpendicular moment arm to the point O, okay, that's going to be that distance that I see here. Okay, so that's going to be a distance of 2 meters. Okay, and if I use the right hand rule, this is going to produce a rotation that is counterclockwise. Okay, so if I do this, then this is going to be mb v0 times the distance of 2. Okay, then plus I'm going to have from integral t1 to t2, go to the impact relevant free body diagram. What is the distance from the point of the ball to the point O? Okay, what is that distance going to be? And that's let me make sure that this is straight. Okay, and that distance is going to be the same distance here, which is 2 meters. But if I use the moment direction, this is going to produce a clockwise rotation. So this is going to be minus fc times 2 dt. Okay, this is equal to, I go to my momentum diagram at time t2. As you can see here, what is the perpendicular moment arm from the location of the ball, the linear momentum of the ball, all the way to where the pivot is sitting. Okay, that's hang on a minute, this has to be a straight line, right? And that's going to be a distance of 2 meters once again. Okay, and that's probably the same story for mpvp prime as well, if you can see that. So this is going to be 2 meters, and it's going to be a counterclockwise rotation as well. Okay, so this is going to be mbvb prime times 2. Okay, and then I'm going to do the same thing. Okay, pendulum about the point O. This is fairly easy to begin with, right? Because when I look at the pendulum at time t1, nothing is going on, so that's going to be 0. And then I do the integral t1 to t2. I look at the impact relevant free body diagram of the pendulum, and I see, okay, that is going to be fc times a distance of 2 meters. Okay, so this force fc is what I'm looking at, times the distance of 2 meters to the point O, counterclockwise, as you can see by using the right hand rule. Align the fingers of your right hand with the force. Your palm is facing the point O. Curl your fingers. Thumb comes out of the page. So this is a counterclockwise rotation. Okay, so this is going to be plus fc times 2 dt. And then I know from before that the distance from vp prime to O is, or mp vp prime to O is still the distance 2 meters, and that's a counterclockwise rotation as well. Okay, so this is going to be mp vp prime times the distance of 2. Let me call this as equation 3. Let me call this as equation 4. If I add equation 3 and if I add equation 4, what do I end up getting? mb v0 times 2. And then you see this plus fc dt minus fc dt. So this is t1, t2 minus fc times 2 dt. I'm going to have integral t1 to t2 fc times 2 dt. These are all things on the right hand side. This is going to be equal to things on the left hand side. mb vb prime times 2 plus mp vp prime times 2. And one more thing I know in this problem is, because so first thing is, of course, I can cancel off this one, and I can cancel off that one as well. Okay, one more thing I know in this problem, we also know that vp prime is equal to vb prime because the ball sticks to the pendulum. Okay, so which means that in this situation, you see that since the impulses are cancelled off, we have have conservation of angular momentum about the point O. Okay, because you see that the angular momentum before impact is equal to angular momentum after impact. Okay, so this is conservation of angular momentum. Okay, and what else can we say here? So now I can find out, since VB prime and VP prime are the same, I'm just going to say that they're just both equal to some V prime. Okay, so I'm going to say that VP prime is equal to VB prime is equal to some V prime. Okay, so I'm going to just substituting. So mass of the ball is M. Okay, so I have, first of all, let me go back and say this is MB V0 times 2. This is equal to MB VB prime times 2 plus MP VP prime times 2. And if I just rewrite this statement, this is angular momentum before impact and this entire thing is angular momentum after impact for the system. Okay, this is angular momentum before impact for the system as well. Okay, so we have conservation of angular momentum about O for the entire system, not for the individual ball or the pendulum. It's for the system only. For the ball or the pendulum, you see there is no conservation of angular momentum here because the impulse is not zero. Okay, so that's something that you got to understand. Angular momentum is conserved only for the system, which is the ball and the pendulum put together, not just the ball or the pendulum alone. Okay, so once I have this, then here is what I can say. So MB is known to me, so the mass M V0 times the distance of 2, then this is going to be MB once again, so M times V prime times 2. I'm just going to say VB prime and VP prime are the same. Then this is going to be 2M times V prime times 2, which means that V prime is essentially going to be V0 by 3. Okay, so this is the velocity of the bob after impact, and also velocity of the ball after impact, because they're sticking to each other. Okay, so that's something that we know. Okay, now I go to the work energy part of the problem. Okay, so now look at using work energy principles. For the event after impact to maximum deflection. Okay, so which means what I'm going to do is this. I'm going to draw the event right after impact, and then I'm going to draw the event at the maximum deflection position. Okay, so look at this. So here is my pendulum system. Okay, so this is the string of the pendulum, and then I'm going to draw one more thing right after impact, and right after it has reached the maximum angular location. That's not a straight line, so well, let me try doing it one more time. My pen is getting a little unwieldy here today for some reason. All right, that's better. Okay, so I'm going to have something here. Okay, and then I'm going to have one more thing here. So both of them are stuck together, as you can see, and I'm going to give a different color to one of them. Okay, so let's make this a different color. Okay, so as you can see here, they're both stuck together, and I'm going to copy these two guys and then paste them again without this guy here, and then bring them here. Okay, so this is the ball and the pendulum. Okay, so this is the ball and the pendulum stuck together. Okay, which means that each of them at that point are going to have a certain velocity, right? So this is the velocity of the pendulum, and then this is the velocity of the ball, right after impact. Okay, this is the situation. So this is right after impact. And then I come to the position where I see that, okay, now both of them have reached a position of maximum angular deflection. I'm going to call that position as theta max. What is the velocity? At the maximum angular deflection position, the velocity of the bob and the pendulum is going to be zero, right? Because they're going to now start trying to turn around, which means that if I write out this one, okay, if I say this is, so this is both V prime, okay, so this is also V prime, which we just found out is V naught divided by 3. Now here the velocity of the pendulum is 0. The velocity of the ball is also 0 at the maximum angular deflection position. Okay, so this is at maximum deflection position. Okay, so I have the two positions done. Okay, so I can maybe call this as position I don't know, 2 and position 3. So this is position 2, this is position 3. Okay, there is no mention of friction and so on. And here is what I can do also further is that I need to choose a datum. Okay, so I'm going to choose a horizontal line here as my datum. Okay, so this is my datum here, and I can see that immediately when I look at the height at position 2, it's going to be below the datum. Okay, so which is going to be a negative height here. Okay, so this is height h2. h2 is going to be below the datum. Okay, this is a distance of 2 meters. And then here, what is the height going to be? I have to be a little careful. Okay, so from here I complete this triangle. Okay, this is a distance of 2 meters here, which means that the height which I am interested in is going to be this height h3, and it is very obvious to see that h3 is going to be 2 times cosine of theta max, is 2 times cosine theta max below datum. Okay, and then here h2 is a height of 2 meters, also below the datum. Okay, so we have all of these done, and now what I'm going to do is apply the work energy theorem, okay, between position 2 and position 3 right after impact, and then at the maximum deflection position. So, and what is the work energy theorem? So I have u 2 3 others plus potential energy due to gravity at position 2, potential energy due to the spring at position 2, kinetic energy at position 2. This is going to be potential energy due to gravity at 3, potential energy due to the spring at 3, and then kinetic energy at position 3. I'm going to knock off many of these things. We don't have a spring in this problem at all, so that creature goes to 0. Then kinetic energy at position 3 is 0 because you see that I'm reaching the position of maximum deflection. U 2 3 others is 0 because there is no friction in the problem, or no friction or any other applied force. Okay, this is because there are no springs. Okay, you can see that now using this work energy technique has become so easy. Okay, now I just start plugging in what I'm going to see. Gravitational potential energy in both the cases is negative. Okay, so in the second case it's minus 2 times mg, third case is minus 2 cosine theta max times mg. Okay, so I'm going to start writing it out. So potential energy due to gravity at 2 for both the ball and the pendulum. Okay, so that's something that you want to be careful. So I'm going to rewrite my statement now. So PE G2 for the ball, PE G2 for the pendulum combined together, plus KE2 of the ball, KE2 of the pendulum is equal to PE G3 for the ball, PE G3 for the pendulum. Start substituting. So this is going to be minus m times g times 2 minus 2m times g times 2. Then this is going to be half times m times ke2b is going to be v prime square plus half times 2m times v prime square. And on the right hand side, I'm going to have PEG3 of the ball, which is going to be minus mg times 2 times cosine theta max, and then minus 2 mg times 2 times cosine theta max. Okay, so this is what I'm going to have in terms of the potential energy on that other side. And I can get rid of some of these common terms here, which I can see. Okay, first of all, this mass term is gone from pretty much all of these things here. Okay, and then I can start cleaning things up. Okay, so let me say that, okay, g is 9.8 meters per second square, and if I clean up everything and if I say that the length is 2 meters, so say so L is 2 meters, which is given, and then G is 9.8 meters per second square. So this 2, I'm just going to write it as L. So if I do the simplification, so after simplification, here is what I end up getting. Okay, I'm going to end up getting cos theta max is equal to, and V prime, V prime is V naught divided by 3. Okay, so we know that, right? This is from the impact event. Okay, so after simplification, here is what I'll end up getting. Okay, so cosine theta max is going to be 1 by 3 times G times L, okay, which I'm going to write in this way, and this is going to be 3 times G times L minus V naught squared by 6. Okay, this is what I'm going to end up getting. G is equal to 9.8 meters per second square. L is equal to 2 meters. If I do the substitutions, I end up getting cosine theta max is equal to the 3gl and 3gl will cancel off. So this is going to be 1 minus V naught square divided by 3gl. So if I look at that, that's going to be 18 GL. Okay. All right. And this is the relationship between theta max and then V naught. Okay, so this is the relationship between theta max and V naught. Okay, this was the thing that we were supposed to find in this problem. Okay, so very briefly, since I have like 2 minutes left before it's an hour, go back to the main problem. The main problem was that, okay, here was a pendulum sitting there minding its own business. A ball comes and strikes it. Find the relationship between the velocity of the ball and the maximum deflection. Okay, what do? I model the impact event as using the ideas of linear impulse momentum and angular impulse momentum. And after that, I say, okay, after the impact, I have to see the maximum deflection so I can make use of work energy techniques. Making use of both of these, I come across figures which are called the momentum diagram. Then I come across a figure that is called as the impact relevant free body diagram. And then we just showed that, okay, if you have a force like gravity or any other applied force, it's not going to cause any effect on the impact relevant free body diagram because its impulse is going to be pretty small or negligible. Okay, so once you do that, you get the velocity right after impact by making use of linear impulse momentum and angular impulse momentum equations. Okay, and then once you get the velocity after impact, which is what we obtained right here, V naught by 3, then I can go back and do my work energy theorem here at position right after impact at maximum deflection position, make use of the work energy theorem, and then I can cancel off some terms, and then eventually I end up with this relationship where G is 9.8 and L is equal to 2 meters. Okay, thank you for your patience. I really appreciate that. I know this is a slightly longer problem, but I wanted to make sure that I'm conveying all the ideas properly. Okay, take care of yourselves and stay safe. Bye-bye.